So welcome everybody. Welcome to the session 2B, Primary Resources, Impacts Monitoring and Assessment. My name is Roland Weber. I'm chemist from Germany, working since 28 years on persistent organic pollutants, the last 17 years for Stockholm Convention. And at the moment, I have a project for the World Resource Forum in Ivory Coast on e-waste and end-of-life vehicle management. This means secondary resources. So I'm not an expert on the primary resources, but today we have 5 experts which will present on primary resources. And I would like to hand over to my other chair, Pauline.
Thank you very much, Roland. I'm Professor Pauline Deutz. My field is human geography. I'm in the Department of Geography, Geology and the Environment at the University of Hull in the UK. And for also some 20 years, I've been working on what we now call the circular economy, so means for resource efficiencies. So know more about me. If we could go to the next slide, please, Antonio.
Yes.
So a reminder for everyone what the format of the session will be. Everyone is welcome to put questions, comments in the chat. Each speaker has 5 minutes and we'll go through each talk in turn, then have a discussion with questions and comments for all the talks after that. And at the end, we will remind you again what the voting procedure is, hoping that you may be selecting one of the speakers today for your favorite so far, at least. Thank you. We could go to the next slide, please.
Yes, and with the next slide, we come to the first speaker. That's Dr. Stefan Giljum. He heads the research group on global resource use at the Institute for Ecological Economics of the Vienna University for Economics and Business. And his research focuses on global assessment of natural resource use, environmental impacts, and the link to globalization, trade, and developmental issues. So he will present himself, the slide, and the whole session is from his group, from the Vienna University group, and the presentations are linked with each other. So please, Stefan, you can share the screen and introduce to the topic.
Yeah, thank you, Roland, for the introduction, and welcome everybody to this special session on the FinePrint project, which is a project funded by the European Research Council. So in my presentation, I will provide an overview of the project in general, which provides the framework for the 4 more detailed discussions that will follow afterwards. The starting point of the FinePrint project was the observation that in the last 15 or so years, a lot of progress has been made with regard to constructing supply chain models of the global economy that allow us to calculate the so-called footprints of our consumption. However, we think that most of the models still fail to appropriately assess the environmental impacts related to resource extraction. And why is this the case? Because most models still operate on the aggregated national level. However, as we know in reality, the environmental conditions, also the social conditions, they differ quite a lot within the extraction countries. So just taking one example here on copper mining in Chile, if you assess the water implications, the water scarcity impacts of copper mining and refining, it certainly makes a lot of difference whether the activity takes place in the north of the country, in the very dry Atacama Desert, or in the more temperate regions in the south. So if we work with and stick to aggregated national impact factors and information, we over or underestimate the actual local impacts that also relate to our consumption of products and services. So the objectives of this 5-year project FinePrint is to develop new methods that allow us to assess the global flows of raw materials and the related impacts using a high spatial resolution. So zooming into the countries where resource extraction actually takes place. So we do this, we realize this by linking spatially explicit data on raw material extraction and the related, in particular, environmental impacts to the models that tell us something about the supply chains, the manufacturing of the products, and all the way to final consumption. We want to identify what are the distant drivers, for example, which economic sectors, which product groups, which consumption areas actually drive these distant changes and impacts in ecosystems and communities, often located on the other side of the planet. And finally, we also want to compare the impacts along different supply chains, but for the same products, in order to identify whether we have any options to reduce the negative impacts by switching from one source region to the other region. The implementation of our project builds on two major blocks of work. The first block is related to the assessment of raw material extraction and environmental impacts on a global scale and on a high spatial resolution. And the second pillar is the development of models that allow tracing or depicting the subnational trade and the international supply chains all the way to final consumption. So we start with the mapping of where the extraction of different materials take place. For example, with regard to mineral extraction maps, we particularly look at metal ore extraction and coal extraction using official statistics and company data in order to locate where resource extraction is actually taking place. We also work on the impacts, assessing the impacts related to mining. Partly we use remote sensing data, so satellite-based data, as we will hear in a few minutes. For example, we are looking at the land use of the global mining sector, the deforestation impacts, or the water input required for mining and processing materials. And we perform statistical analysis in order to evaluate where on the globe we find the hotspots related to high impacts of resource extraction. So that's the part one of the project. And the second part relates to the international trade and supply chain models. We basically focus on two areas of commodities. One is biomass. We won't hear a lot about this today because it's not the major issue of the conference, but we are developing physical, what is called multi-regional input-output models. So basically representations of the global trade and processing of biomass products, which we also downscale to the subnational level using, for example, production data or trade and transport data. And the second major commodity group we are focusing on with regard to trade and supply chains are metal ores, where we also develop physical global trade models that we also move to the subnational level in order to link it to the place where the extraction takes place. And finally, the two parts of the project, of course, need to be linked. Here, we mostly work with a proportional allocation where we allocate between the subnational entities, for example, a municipality or a region in an extracting country, and the grid cells where the actual extraction takes place. Yeah, just to give an overview of what you can expect in the next few minutes. So Victor Maus and Stefan Lutter will focus on our work related to the environmental impact assessment of mining. Then Sebastian Luckeneder in his presentation will show how we use statistical and econometric methods to investigate the environmental impacts, but also the socioeconomic consequences of mining activities. And finally, Hans-Peter Wieland will focus and present in a nutshell our work on the physical trade models with a focus on metal ores. And just to point out that we also have two posters related to the FinePrint project in the poster session. So Simon Jasanski presents his work on how to create global maps of mineral extraction. And Stefan Drissek in his poster presents how we spatially, in a spatially explicit way, calculate biomass footprints, taking example of soybeans in Brazil as a showcase. So these are all the contributions to the World Resources Forum this year from our project. And final slide is on the potential use of results. What are the results hopefully valuable for? Well, we are already in cooperation with a lot of colleagues from academia itself, working, for example, on the relations between the drivers and the local impacts in hotspot resource extraction countries. But we also think that we can provide a valuable input for policy design and policy monitoring, for example, in the area of resource extraction governance. Here we are, for example, in contact with UNEP, so they are interested in taking up our assessments of the impacts of mining. We also think that business and industry might be interested in this type of research, knowing more about the environmental impacts of resource extraction on a global scale, and also providing and using information about the supply chain-wide pressures and impacts. And finally, we also hope maybe in the medium term to contribute to raise the awareness by consumers of the global impacts related to our consumption in order to trigger changes in behavior and lifestyles. Yeah, all the information about the project you find on the project webpage, fineprint.global. We also follow an open science approach, meaning that all the codes, all the data, all the results are openly available. And we have a GitHub repository for that purpose. And yeah, we also feature the project on ResearchGate. So if you're interested to follow, I invite you to connect to us through this channel. Thank you very much.
Thank you, Stefan. That was very interesting. Could I invite Victor to share your slides, please? And I will introduce you in the meantime. So Dr. Victor Maus is the next speaker. He's a researcher at the Vienna University Institute for Economics and Business and the International Institute for Applied Systems Analysis. His research areas are geoinformatics and spatial data science with applications to environmental monitoring and modeling for sustainable development. Thank you very much. I can't hear you, Victor.
Victor?
Victor, we can't hear you.
Before we could hear him. Yeah. Maybe one time remove your headphone and directly speak to the computer. That sometimes
we might also move to Stefan Lutter maybe first, and
okay,
because the order is not so important.
Okay, now then we have first the third presenter, Stefan. No, the third would be Sebastian Luckeneder. Yeah, so Mr. Sebastian Luckeneder is a secondary year PhD candidate at Vienna University of Economics, same group, and a teaching and research associate at the Institute for Ecological Economics. His main field of scientific interest include spatial statistics, resource extractivism, development economics, and political economy. Yeah, Sebastian, then you do your presentation first.
Yes, hello, and thank you for the introduction. Can you see my slide?
Yes.
Okay, perfect. So yeah, welcome also from my side. Thanks again for the introducing words. So my presentation is on basically how we can use geospatial data in combination with quantitative methods in order to better assess the environmental, but also social and economic risks and impacts of mining activities. Talking about risks and impacts, well, let me first of all, observe that these are not quite the same things. On the one hand, contextual risk is defined by the broader social or environmental factors around mining operations. And considering contextual risks, such as if mining takes place in high or low biodiversity areas, or close or far from protected areas, can indicate where harmful impacts may be more severe than elsewhere and help us to identify potential high impact areas. The actual mining impact, on the other hand, refers to the actual causal links between mining and, for example, forest loss and in turn biodiversity loss, for example. And our approach is now to basically use geospatial information to better inform both of these strands of assessment. Starting with the monitoring and contextual risk assessment. Well, we did the first thing we worked a lot on was basically to create and compile a lot of data that is geo-referenced, and we were referring to point data, so basically the exact coordinates of mines and other information on that, as well as polygon data such as concession areas or actual lands that is occupied by mining. And I think Victor will, in his talk, give a bit more information on that. And then, for example, we worked on one pilot study that I mentioned here, where we used information on 3,000 individual mines and 9 different metal ores and compiled a data set with yearly information for the past 2 decades, where we even estimated the actual extraction volumes per mine. And then we used this data, and this brings me now to the risk assessment, to intersect it with other environmental and socio-economic geospatial layers. And for indication of vulnerability, we used layers on biodiversity, protected areas, and water scarcity. And in turn, considering also the development over time, then provides new information, new insights into global extraction trends, disaggregated to whatever set of spatial layer we want, such as distance to protected areas or biome categories. Such an analysis, however, basically doesn't say much about any causalities in there. And this brings me actually to the next part, the statistical modeling and the estimation of actual impacts of mining activities. And there, our main motivation actually lies in the observation and the demand for an assessment of cumulative impacts of mining activities. So currently there is a lively debate on assessing spatial and temporal spillovers, which also need to be considered when we talk about impacts. For example, there is a study by Laura Sonta, who finds that mining indeed indirectly affects deforestation in the Brazilian Amazon up to 70 kilometers beyond mining leases. And also, from an economic perspective, where I have more my background in, we have this debate on whether or not mining actually somehow creates beneficial economic agglomeration effects, such as via employment creation, where the impacts spill over to neighboring regions. And our approach is now to employ basically spatial econometric techniques, and I will not go into detail with the modeling, but the basic idea behind that is to impose a spatial structure on our data where close units, close observations are more related to each other than distant ones. And this allows us to compute basically direct and indirect impacts. And one application we have on that, I'm working currently on an application, is on regional economic and land cover effects of mining activities in Brazil, where the unit of observation is the Brazilian municipality, and we created a panel data set, also including a lot of other information on socioeconomic variables in order to basically link mining to municipality level growth rate, economic growth rates, but also municipality level deforestation trends. And just as a preliminary result, we indeed find direct as well as indirect impacts. And interestingly, we find that mining indeed increased economic growth in mining areas as well as in the neighboring areas in Brazil previous to 2010. But we also find that this economic effect disappeared since then, whereas basically the trade-off effect here, the negative effect on forest cover, is very clear and very robust, almost along all the time, directly and indirectly. Yeah, and since I'm already quite advanced in time, sorry for that, I just go briefly over the main takeaways from our experience that we have collected so far in this modeling. Well, we see that using spatial data has indeed high potential for better mining management and policies. On the one hand, with regard to better monitoring and taking into consideration spatial heterogeneities, as Stefan also referred to in his introductory presentation, but also with regard to the modeling of cumulative impacts. And then, and I just very briefly skim that, we also encounter several challenges and limitations in this process. Most of them with regards to the data, because it's really, trust me, very tough to compile these spatial data sets. There is limited public information at the mine level also, in terms of more additional information such as extraction volumes and so on. And maybe one final point I want to mention is also that for us with economics or statistics as background, it's really important to foster interdisciplinary collaboration, especially with people who are, I would say, mining experts and working in the field and help us with these assessments. Yeah, and that's it. Thank you.
Thank you very much, Sebastian. Victor, would you like to speak next?
Yeah. Does it work? Do you hear me? Hello?
Yes.
Yes, you would. Well, please go ahead and share your slides.
Okay, thank you. Okay, thank you for introduction, and also thank you for...
I hear you, but very quietly.
Oh, really? I don't know what that is.
Now it's better.
Yeah, okay, I'm gonna shout a bit here. The neighbors can complain a bit. Okay, thank you for the patience with these technical issues. So I'm gonna be talking a little bit about the role of the Earth observation and satellite imagery in the data collection and spatial split assessment of mining extraction or raw material extraction. As we have heard in the first two presentations, like environmental impacts and also social impacts are unevenly distributed in space. And there is also a challenge that Sebastian just mentioned, is the lack of openly available data, geographic data on raw material extraction. This is a real challenge that we face. And perhaps the only source or the only way to overcome this today is with satellite Earth observations. And for the mining sector, it's particularly challenging to get information. And for that reason, we have produced, let's say, the first ever global map of mines for land use of mining areas globally. And this data set is based on visual interpretation of satellite image, high resolution satellite image. And it is already in a second version now. We produced two versions of this data set. We can see in this map in the background here all the locations where we have collected data. And yeah, the first version is already openly available. And the second version of the data, which covers double the area as the first version, will be available soon. And I'm going to be presenting a few of these results here in this today's talk. Here's an overview of this land use of mining globally. So we have produced in the second version of the data more than 45,000 mining locations mapped visually. So it was quite a work, and I have to thank to my two students who worked hard on this. It was Jason and Robson in Brazil. And we covered an area of mining of 100,000 square kilometers. And as we can see here, this is unevenly distributed across the globe. We have only 15 countries covering 80% of the mapped area. So it's a quite uneven distribution in terms of countries. As we can see, the most prominent ones here, Russia, China, Australia, United States, and Indonesia, Brazil coming after, and so on. But when we look into some environmental aspects of this data set, we also see some uneven distribution of impacts here. We can see when we cross this data set with biomes, we see that around 30% of the mining area, global mining area, is actually within tropical and subtropical moist boreal forests, which have a high biodiversity value. And we can see in this map here an example of these polygons mapped in purple here, where this is mostly small scale or mostly artisanal gold mining in the Brazilian Amazon. Further than that, when we look into, for example, deforestation or forest cover loss, we see that also the tropical forests are the most impacted ones. We see that 62% of the forest cover loss taking place within the mining areas that we have mapped has happened inside of the tropical and subtropical moist boreal forests biome. So this shows a clear uneven or heterogeneity in the environmental impacts caused by the mining sector, and also the important role that the remote sensing and satellite image can do to improve the assessments or spatially split assessment of raw material extraction, to provide better information to assess global supply chains and therefore fulfill the goals of our project here. I would also add to this that this data set, as it was produced as let's say more kind of a craft work, a handwork, this also provides a very nice asset that can be used for training machine learning or deep learning algorithms or more sophisticated methods that could automatize the process of mapping the whole global mining sector. And with this, I would like to close the talk. If you want to see the data that's already available, you can visit the fineprint.global/viewer. You can have a look at the mining polygons that are currently available, version 1, and the version 2 of the data, which I just talked now, is going to be released hopefully over the next 1 month or 2 months. Thank you for your attention.
Thank you very much for your talk, Victor. I would like to invite the next speaker, Stefan Lutter, if you would like to share your slides, and in the meantime, I will introduce you. Dr. Lutter is the Deputy Head of the Research Group Global Resource Use at the Institute for Ecological Economics at Vienna University of Economics and Business, which is among the leading European and global research groups in the field of environmental accounting, environmental economic modeling, and resource efficiency. Thank you, Stefan. Over to you.
Thank you very much for these introductory words. I hope you can see my slides.
Yes.
That's cool. Thank you very much. So my talk is about the estimation of water input in the mining industry in Brazil. As you see, quite a few of our case studies include or focus on Brazil. This is to one part on purpose, to the other part on occasion, because in this regard, for instance, it was the luck we had of a very good collaboration with colleagues in southern Brazil who are experts in water accounting in the mining industry. So just to provide a background, as we have seen already in the previous talks, mining plays a really significant role in the Brazilian economy. And this is the fact since the colonial times. Mining is also a particularly water-intensive activity. Having said so, it's in comparison to other sectors, the amounts of water are perhaps lower, but the impacts, the local impacts are similar or even larger than in other sectors. We also can see that there is a rapid increase in extraction, which brings along with it a increasing pressures on the local resources. And interestingly, but also comparable to other resources, really site-specific data on water input and water management are rather scarce if we look at the global scale. And so the intention of this work here is to propose a methodology for how to estimate water input in mining at a higher geographical resolution. We focus here on Brazil because our take was that data availability is better than in other countries, and especially the auxiliary data available is helpful, so indeed auxiliary. We focus on 3 key metals, which are iron ore, aluminium ores, which is bauxite, and copper ores. And the idea is to derive water input coefficients from company reports, from governmental sources, and from the literature. So what's the main process or the main approach here? We start with quantifying metal production at the mine level. This is already quite a challenge, as we've heard also from Sebastian. So the first question we ask is, okay, for the mines at focus, and I've forgotten to mention that we are looking at 100 mines here, more or less. The large majority are iron ore mines. So do the companies running these mines report production numbers? If yes, then great, because that's the primary source. If not, we estimate these production values via national and regional reports and via a specific data source on the taxes paid by the different companies for mining in Brazil, which was quite a good data source, actually. Once we know how much is produced in each mine, we start identifying the water intensity of each mine. So how much water is used per unit of raw material produced. And here we take the same approach. We have a look at if there is a water coefficient reported by a company. If so, that's the best case, then we use that. If not, we look if a corporate as such, if the corporate is providing an average water coefficient for its activities, for all its activities in Brazil. And if that's not the case either, then we go, then we applied coefficients based or taken from the literature. And then as a final step, we use the production numbers multiplied with the coefficients and get an estimate for the water inputs at each mine site. So here we are already at the results. First, we might want to look at the right map. So here we see the comparison of rain intensities in Brazil with the water input in mining in the different regions, and we see that the results paint a quite diverse picture. So we have at the one hand a lot of water input in areas where it's raining anyways. So there the challenge to be tackled is rather the management of too much water, right? And then we have other cases in the southeast where we have already rather dry areas where a lot of water is used for mining activities. So it can be supposed or assumed that in that areas it will rather be a question of if all the stakeholders involved in the region have enough access to water. And if we look at the left map, we see it more metal specific, which of the metals are especially water intensive, or which of the metals use most water in comparison to the other two. And we see, for instance, in the northwest, the water input would be similar distributed, but in the southeast, iron plays the major role. So finalizing, what are the main takeaways of our results? We can see that water input for bauxite, copper, and iron ore mining decreased over time, which might have different reasons, and I'm getting to that in a second. We see that most water was appropriated in the north, in the Pará states, and in the southeast, in Minas Gerais. And especially in the southeast, large water input is needed in a setting of reduced rainfall. So there water scarcity is rather an issue to be tackled. What we have also seen, and that was a very valuable feedback from our reviewer, actually, one of our reviewers, is that water input, of course, is strongly dependent on the local rainfall and on local process requirements. So if there is, for instance, wet tailings or dry tailings techniques, or to what extent water is recycled. And this, of course, will have to be taken more into consideration in the future, provided that data on these process requirements will be available. Site-specific data on different types of water flows is still scarce. So in many cases, you get just one number without knowing what type of water flow it is or for what it is used. And we are sure, or we have seen, that mine-specific research could provide more insights in meaningfulness of generalized assessments and generalized assessments of a larger number of mines. And finally, last but not least, we have also seen that accounting standards for the mining industry or for water input in the mining industry are there, but they should be applied to to a larger extent. We see that data availability is still extremely scarce, and this makes it very hard to find the data and then to do proper water management from a political point of view. We assume that from a mine or from a company point of view, the knowledge and the data is there, and they know quite well what has to be done and where to take action. So that's it from me. Thanks a lot for your attention.
Yeah, Stefan, yeah, thank you very much for the interesting presentation. Then we come to the last presentation of the session. That's from Hans-Peter Wieland. You can share your screen, Hans-Peter. He is a PhD researcher, also at the Institute of Ecological Economics of Vienna University. And his talk will be about rebalancing resource disparities between partner countries. So please, okay. Hans-Peter.
Thank you, Roland. I'm assuming you can hear me and see my slides.
Yes,
okay.
Yes.
Good, welcome, hello. So I'm closing this series of FinePrint presentations, and as Stefan has already mentioned in the first part, the overall, the overarching goal of FinePrint is to basically trace very local environmental impacts and pressures of mining across global supply chains. And our philosophy, the way that we are trying to do this here, is to first, we always start with a very global country by country model, and then using all these subnational data that we are nesting into this global model. But before I'm going to talk about that, just in order so that we are all on the same page, these slides, yeah. So here, basically, here we can see the general layout of these physical tables. This is an example for 2 regions and 3 processes. And in what I'm showing you here, and later on, I'm always referring to our first model, which is the iron and steel model. These physical tables, they consist of 3 different parts. First, in blue, we are having here the flows of intermediate inputs, which shows how peak iron and liquid steel is used. Second, we are having the final use block here in green, which shows the amount of steel that is contained in cars, buildings, and other final consumption products. And thirdly, we are having boundary inputs and boundary output flows, which come from outside of this steel system here. So we are referring here to flows like coke, ore, scrap, and air. And on the output side, we are also having flows like emissions that are going back to nature, or things like slag. This is a mass balanced model. So this basically means that our column sums and our row sums, the total inputs and total outputs, they must match. So with such a physical table, we are able to basically model the supply chains on a very detailed regional and process level. And I want to make this point by showing you here these Sankey's for two selected countries. The first one is Germany, where we see all the direct and indirect flows that are associated with the final consumption of steel in Germany, which is here on the right side. So all these flows go from left to right. We are having here ores, pig iron, steel castings, and all these things. With our multi-regional model, we are now able to analyze detailed where are these flows taking place. I would say that. So basically, purple shows you here flows that are situated within Germany. Green are flows that are situated outside of this country here, Germany, and yellow are then the trade or import flows. This is quite informative if we compare it to other countries. And here I'm showing you a second country, South Korea. I selected these two countries because their material footprint is quite similar. They both having an iron ore footprint of about 60 megatons or 63. Both regions are similar, that they are not having large mining, iron ore mining areas within their countries, but the way that they are sourcing ores is actually quite different. You can see, for example, here yellow shows trade flows. South Korea is importing a lot of ores, which is why they are having quite a strong steel sector within their country. On the other hand, Germany is here importing larger flows of finished steel. So we can see here some different patterns which can be quite useful in understanding what is happening here. After showing you these small teasers, I just want to take stock where we are now. At the moment, we are having a prototype for the global flows of iron and steel, which differentiates 32 regions. The paper is forthcoming in a couple of days, and the first tables are already available on the internet. I must mention here that this laboratory is based on the IELAB technology, which has been developed at the University of Sydney, and in its core, it's actually an constraint optimization tool. And with this tool, we are able to, I say, efficiently build these big models, even when our very data basis is quite scarce. The next steps are then to create these global subnational tables for iron, copper, and aluminium, and extending these pipes with proxy information on the mining impacts. I can only show you now a basic example how these tables will then look like. Such a subnational global table means that we are having at least one region within this global table which refers to a subnational region. And here we have just chosen for this hypothetical case here, Western Australia, and the second region would be rest of the world. And in the second step, we are extending such a PIAT with all these subnational information by intersecting all those pressures that my colleagues have presented before with information on the state of the local environments. For example, the land use data Victor has shown us could be disaggregated into species-rich and species-poor biomes, the water use data into water scarce and water abundant biomes, and so forth. So this extension then basically is a proxy for the impact risk. And with this model, we can then analyze the consumption drivers that put the most pressure on such risky areas on the subnational level. So this is then basically the end of my talk. Looking forward to some questions. Thank you.
Thank you very much. I note we have 3 minutes left. So Antonio, perhaps you could put the slides up so people can be thinking about the voting procedure while we see if there are some
I can also do that.
questions. At the minute, I don't see any questions. So I have a couple, and I've been trying to frame in my head what the best one to ask would be. And I guess I'm curious about the data that you're using, the ground truthing data, as I believe my remote sensing colleagues might call it. So you've shown us and analyzed an impressive sort of wealth of data that we can look at the national scale in particular. But perhaps one of you could say something about the local collaboration that was mentioned and how you've interacted with people on the ground. Because there's some quite important issues there around the biodiversity or the local water use or the local economic influences. How have you incorporated that local scale knowledge, let's say?
Yeah, just one of the speakers.
Ooh, and I'm happy for anyone to have a go at that question.
I can comment a bit on that. Like in the case of the land use data set that we produced in a global scale, and we don't have any local collaboration on that. We did all like remotely. I have two students that work with me in Brazil, but they are not like working on mining regions, or they are not experts on mining, but they are remote sensing experts that were working on that. Yeah, we didn't yet outreach any local like stakeholders or communities that would be working on mining.
Okay. Maybe I can add on that. I think it must be emphasized that the FinePrint is kind of a top-down project from its very origin. So our ambition is to really provide new data, new assessments on the global level, being fully aware that we are losing a lot of detailed information that is available in the communities on the ground everywhere in the world. So I think that's complementing many other also case study oriented work that is being implemented in mining, in agriculture, in many fields. But we are trying to complement this, giving a frame by providing really global scale assessments as a background against which others hopefully can use our results connect it to detailed local knowledge in countries around the world and move forward.
Thank you very much. I think that we have to close the session and go to the next ones that we may be planning to.
Yeah, but I mean, to highlight that everybody should go to the WRF app, yeah, and then vote for the best speaker and also vote for the best presentation. So you have 2 votes. I just tried it on the WRF app. It worked. So thank you very much. Yeah, for your great study. I also would have had one question. If you were considering to include, let's say, drinking water wells and groundwater in respect to pollution, or if this could be done, but maybe we can discuss on this another time after the session.
Yes, thank you all very much. Very enjoyable talks and a very impressive study. Thank you.
Thank you. Have a good afternoon.
Thank you. Bye.
Bye-bye.
Thank you.
Bye-bye.
Thank you. Bye-bye.
Bye-bye.